Flow Talks Design, hosted by Tietoevry Create.
It's really great to see so many of you here this early on during the day. We're honored to be the opening act for this stage today. My name is Anna Ulanka, and I'll be guiding the conversation today. And over the next hour, we'll have 3 design veterans who explore the intersections of the digital and physical world. We'll learn how design can draw inspiration from nature's systems, build better cities, and tackle challenges posed by technology, all while keeping the human experience at the center of it all. This event is hosted by Tietoevry Create, which is the technology partner of Flow. It's also behind some of the technological tools you'll see around here, like the Flow app, which I highly suggest everyone to download if you haven't already, as well as the material and carbon footprint budgeting tool developed in collaboration with DMAT, helping to support the development of an ecologically sustainable event. Now, we have a full program today, so let's get started. Our first speaker has over 30 years of experience in design and design-led organizations. Denny Royal is the newly appointed head of global design at Tietoevry, and one of only about 200 experts in biomimicry of his level of training worldwide. In his keynote, Denny will talk about how we can use nature's systems to inspire innovation and adapt to some of the pressing challenges our humanity faces, such as the climate change. Please join me in welcoming Denny.
Thank you. So, truth time. Things aren't looking so good for the planet, for us as a species, for all the other species on the planet, and it's now painfully obvious. And unfortunately, in our arrogance, we are taking a bunch of other species with us. We all are kind of in the program of rendering large swaths of the planet kind of uninhabitable, and it is really starting to impact and become very apparent. And it's finally at a point where we can see what's happening. We are about to hit or have hit multiple major tipping points. Some examples of that. So the Thwaites ice shelf is about to splinter apart probably in the next decade or so. And when that happens, we're going to see just from the ice alone on that piece of the glacier and that head wall, about a 65 centimeter sea level rise. If it destabilizes the entire West Antarctic shelf, we will see roughly a 3.2 meter sea level rise. And when we see that, that's going to displace about 120 million people, homes globally, worldwide, that exist in that kind of high tide zone. We're also seeing other things happen, more 1,000-year weather events. I don't know if anybody paid attention to the last few hurricanes in the Atlantic, but they became much stronger, much quicker, and we're seeing more and more of that. And it's shocking scientists to the point that they are having to put extra levels of hurricane grading into those things now. And we're also seeing a lot more fires. Fire intensity, both in North America, Australia, Europe. We're seeing these things kind of intensify, and we're starting to see mega fires that actually create their own weather. So this problem of climate change lasts for 1,000 years, and it's probably the most important and kind of longest term problem that we have. There's no other problem for our species. Everything else pales in comparison. It's going to lead to more war, more famine, more displaced people, more vector-based diseases. So if we don't do something about it, everything's going to change, or already is changing. So we've crossed a threshold already where sustainability is not really an option anymore. We need to start thinking about what our climate adaptation looks like, and if we're ever going to kind of get out of this 1,000-year problem, we're going to need to think about that differently. So when we think about that, we need to figure out how we really adapt to that reality. When you think about all the species that have ever inhabited the planet, 99.9% of every species that's ever been on this planet has went extinct. And they did that because they were maladapted. So the question is, as a human species, can we be maladapted, or will we be well adapted and actually be able to adapt to the climate change that we've helped create? The choice is ours. However, there is hope. That was a whole bunch of really kind of dire messaging that I opened with. There is hope, and there's a way to think about this. And as designers, we've got a huge part to play in that. We can think about it differently, whether we're doing hard product, whether we're doing digital, whether we're thinking about the built environment. All of those things, we can use our roles to influence how we adapt to climate change and what that starts to look like, and how we think about actually being resilient and regenerative in the way that we think about those things. And this is where biomimicry comes in. So this is the idea of looking at nature to help solve design problems. When we think about all the problems that I just said, when we think about innovation, where does that innovation really come from? Normally it's a few of us standing in front of a whiteboard trying to come up with ideas, and I don't know that those human processes are maybe the best place to be looking and the best way to approach those things. When we do that, we only bring our own biases and kind of what we have in our heads as human beings to be able to have those sorts of solutions and stuff, and I think that there's a better way of looking at that. Innovation is actually one of the oldest processes in the world. Life has been on the planet for 3.8 billion years. The planet has been existing for 4.8 billion years. And there's been innovation happening ever since the first kind of bacteria was formed out of the primordial soup. So we'll do a little thought exercise and think about what that means and all the innovation that's happened over the last 3.8 billion years. So let's compress 4 billion years into 1 year. And think about it this way. Think about January 1st as the day that the Earth is born. And we're going to take a little journey on all of the innovation that's happened. So 4.5 billion years old, the planet's been here that long, the clock has just ticked past New Year's Eve. Not until February 25th does life actually appear on the planet. So that's 3.8 billion years ago. Up until now, it was just primordial soup. Cyanobacteria were some of the first things that were formed, and life began colonizing the planet when that happened. So life equals the first innovation when we think about this journey. So for the first month and a half, 2 months, it's only this bacteria, and CO2 levels are rising in the planet. It's not until a month later, on March 28th, that the next innovation happens. And this is when we start to see photosynthesis. So that's when that first occurs. We start to see the conversion of carbon dioxide into oxygen, and the sequestration of that carbon dioxide really starts to set the tone for life colonizing the planet. And it's also another really cool innovation that happened is that we can start to create energy from sunlight. So that's been happening for quite some time. It changes the rules for living on the planet, for sure. All of April, May, June, July go by, it was only single-celled organisms. And finally, on August 16th, we start to get to multicellular organisms. September 17th, sex happens. And when sex happens and we start to see sexual reproduction, we start to see a bunch of recombinant possibilities. You start to see the mixing of DNA. You start to see a lot of different species start to adapt. And those organisms begin to thrive. They're shuffling the deck as far as what those adaptations look like when we think about life on the planet. It's the beginning of really exponential growth on the planet when that sort of reproduction happens. And then not until November 15th, the fungi show up. They're one of the oldest kingdoms on the planet. And we're just beginning to understand actually how much fungi have impacted life on the planet. When we think about mycorrhizal networks and think of them as almost the internet or information exchange of most plant-based things, and terra firma, those things start to happen, and it really allows colonization of the planet. 5 days later, November 20th, vertebrates show up. And those are the first ones that begin to colonize the oceans. And then November 22nd, a couple days later, land plants begin to emerge. And the fungi had set the stage for that with that mycorrhizal network that I was talking about. And that allows us to start kind of more and more plant-based stuff to start growing on the planet. You start to see different, again, because of the reproduction, you start to see different recombinant possibilities and things happening from an adaptation standpoint. And then November 24th, insects finally show up. And there you start to see even more innovations. You start to see things that can walk. You start to see things that can fly. You start to see praying mantises and those funny praying mantis things. When you think about insects, kind of an interesting fact with those is insects actually take up more biomass on the planet than we do. And as just one species, for instance, ants have more biomass than all of humanity. It's kind of funny because you never really see them that much. You wouldn't think that there would be more of them mass-wise than there are of us. And you certainly don't see all of their trash like you see all of ours. December 2nd, amphibians show up. So they start to kind of leave the water once in a while. And they did precede reptiles. They're kind of coming out of the oceans, coming out of the lakes, going back into the water, and start to colonize a little bit. Then on December 6th, we see reptiles finally, and they've been around since then. Mammals, so our forebears, have only been on the planet since December 13th. We've clicked almost all the way through the year, and there's really no human presence or anything going on yet. Birds have been around even shorter. They've only been around since December 18th. Plants, this is kind of a surprising one with flowers. They've only been around for about 11 days since December 20th. And the reason that there's been such a profusion of flowers is that flowers have a commensal relationship with beetles. There's a lot of beetle species, millions of beetle species, and most flowering plants have some sort of relationship with those beetles. And that over millions and millions of years have allowed us to kind of adapt to that very quickly. December 25th was a really shitty day for the dinosaurs. A giant meteor crashed into the planet and they went extinct. But that's really only about 6 days in that 1 year compressed timeline that we were talking about. So let's fast forward to hominids. When you think about that and you think about the first two-legged species to walk on the planet, when do you think they showed up? Anybody got a guess? Hominids have only been around since 1130 on December 31st. So our ancestors, not even Homo sapiens sapiens, have only been around for about 12 and a half hours. So how long do we think we've been here? How long can we lay claim to the planet? 24 minutes. Humans have been around for about 24 minutes. So think about everything that we've done in that 24 minutes. So agriculture changed everything. It really allowed us to be in place and start to have innovations. And we went from hunters and gatherers to remaining in place and starting to develop a whole bunch of different stuff. So about 1 minute. 10,000 years ago was 1 minute. So we talk about the Industrial Revolution, which is where we base all of our innovation work and all of our innovation thinking on, where we started to do all the amazing stuff with oil, coal, our brains, machines, computers, technology, etc. All the answers that we kind of currently use for living on this planet as a species, not even a full second. So the Industrial Revolution was not a full second. About 200 and some years ago, and we base all of our innovation on that. So think about, are we at the pinnacle of innovation? What have we really done to the planet? And is this the kind of best that we can do? After 3.8 billion years, do we stand proud and say that this is what we've done and this is all that we've accomplished? And I don't really think so. So 1 second of innovation has been where we rely on everything. And as designers, we're being asked to think about bigger and bigger problems. And I think that there's a better way of looking to the future and thinking about where we do those things. We like to think that we've accomplished quite a bit, but what if we looked at nature to actually start to solve those problems? So if we looked at all that 3.8 billion years of innovation and used that, what wisdom could we tap into? Could we actually learn something and think about it differently? And that's where we start to talk about biomimicry thinking as a lens and a framework to approach that sort of work. But in order for us to do this, we really got to think about quieting our cleverness. You know, we all think we've got the answers to everything, and there's a different way of approaching that. So we got to kind of put ourselves back in that childlike mind, be curious about what's out there, and use the library that we have. We're a really young species. Like I said, we haven't been around for that long in that timeline, and there's a lot that we can learn from everything that came before us. So when we think about biomimicry, it's that intersection of biology, nature, and life, along with design, innovation, and technology. And we're really, when we think about that work that I'm talking about, that is the intersection and that's the sweet spot. We think about it as a discipline and a practice and a way forward. It's the way that we think we can adapt to climate change and actually be more regenerative and think about that work. It's an emerging discipline, but it's actually an ancient practice. Like I said, the last couple hundred years, prior to that, most indigenous cultures actually did look to nature to think about how they solve their problems. And it's just when we built the built environment and started to separate ourselves from that, that things really started to change and we got away from those practices and we forgot those principles. So there's a giant library out there. It's right outside our door. And imagine if we started asking those questions and thinking about nature as a model, as a mentor, and as a measure. It's not biotech or bioutilization. It's very different than that. And it's really about the conscious emulation of nature's genius. It's also about thinking about forms and looking at processes and ecosystems as well. You think about the bees, there's all sorts of form and process work going on. They build their honeycombs. It's all additive manufacturing. So think 3D printing. It's not subtractive. Most of the time when we try to build something as humans, we take a block of metal, we carve it up, we do a bunch of stuff with it, and nothing happens, right? We waste. So a couple examples when we think about biomimicry. The Shinkansen bullet train was formed a few years ago, and it came about, they had a problem with the train. Every time it would enter a tunnel and exit a tunnel, it would leave a sonic boom. And that sonic boom caused all sorts of complaints in Japan about what was happening with that. And one of the key engineers on that project was actually an avid birder, and he started to look at the kingfisher. So the kingfisher is really interesting. The way that its head structure is structured, it allows it to go from the two different mediums, right? Two different fluid mediums. It goes from air, one fluid medium, into the water, another fluid medium, and doesn't make a splash. So they started to look at this and think about, okay, what if we designed the front of this train to be the same shape as that? What would that do? Ended up, it doesn't make a sonic boom anymore. The train travels at 200 miles an hour. It's quieter. It's 15% less electricity use now, and it's actually 10% faster than it used to be. Whale power is another example. So humpback whales have these really cool little structures on their fins, on their front fins, called tubercles. And that allows an animal that is 12 to 15 meters long to do about a 5-meter turn when they're blowing bubble nets in order to capture food. So the way that those tubercles allow the things to grip in that fluid medium of water, they started looking at, could we do that with windmills? And could we do that on anything that has a blade on it like that? And they've actually built a bunch of windmills now that have these tubercles on the back of the fins on the propellers, and it allows for much better grip of the air. So it's an 8% improvement of lift and a 32% reduction of drag. It makes those windmills for power much more efficient. Another one that we looked at is Pack Scientific. So fan tech has been around for about 2,000 years. You can hear all sorts of fans behind me here, in my computer, everywhere, and that technology really hasn't changed for a long time. So they started to look at, Pack Scientific started to look at the Fibonacci scale and the way that bull kelp leaves are formed, and started to actually build fans that are in the shape of the spirals for pumping all sorts of fluid mediums. And those reduce noise by about 75%, and they reduce kind of drag and staggering, kind of a reduction of energy use by anywhere from 10 to 85%, depending on what sort of medium they're transferring with those fans. It's also used in software design. This is what we do at Tietoevry Create, is a lot of custom software. One really good example of how to use that is Klaus Matic did a thing called a soft kill option. And so the next time you are driving around in your automobile or flying in an airplane, you can thank the trees for that safety and efficiency of that. So what that software does is every kind of structure in nature, particularly if we think about human bones or we think about trees, material is only where it needs to be. And it's only where it needs to be because material is very, very expensive in nature. So they built an algorithm that you can put any part into, and it will analyze that part and get to the exact right amount of material in the exact right spaces in order to recover off on that stuff. So it's really kind of optimized things up to 30% of the material that was used before is being used now. It makes it much more optimal, makes the cars lighter, more efficient, etc. Another interesting software one, EvoLogix. So they are in charge of building early tsunami detection and trying to transmit radio signals from deep in the ocean is a very difficult task. So they put sensors on the bottom of the ocean that senses these tsunamis when they're about ready to happen and the wave structures coming through, but they had a problem with kind of transmitting that signal through all of that fluid of water. So they started to look at what dolphins do. Dolphins can talk to each other at about 25 kilometers apart. And they do that by sending multiple signals at once. So they overlap signals when they send those squeaks and beeps. And EvoLogix looked at that and really figured out how to do that modulation. So it allows them to project those signals back up and do the tsunami warnings and transmit that signal through the water. It's also very applicable to thinking about the built environment. Most built environments, one of the larger operating costs when you think about it is HVAC systems. So millions and millions of dollars are spent to heat and cool buildings. But they went and looked at termite mounds, and inside of termite mounds, in Africa, for instance, the day to night temperature can go from 42 Celsius to about 3 degrees Celsius. But it only really wavers by about 1 degree Celsius inside of the termite mound. And the reason for that is there's all sorts of little doors on the termite mound that get opened and closed, and each termite has a different temperature threshold that it says, hey, we've reached this temperature threshold, it's time for me to close my door or open my door to make it hotter or cooler on the inside. So the architect of this building looked at that at the Eastgate Mall in Harare, Zimbabwe, and actually built a bunch of little doors that opened at different thresholds, and they have saved about 90% less energy in the first couple of years of ownership of the building. They saved $5.5 million in HVAC costs alone. And the last example is healing. So in the biomimicry space, we started to learn from other critters about how to heal ourselves. One study, they're going around and following chimpanzees. And there's a particular tree, for instance, that they treat themselves called the Veronia genus that allows them, they seek it out when they've got any kind of pinworm, hookworm, giardia, etc., that humans also suffer from. So science has started to follow them around and think about how we can mimic that sort of stuff. So here's the thing. We're all part of nature. We're not separated from it. It's not an artificial construct. And like I said earlier, 99% of the species that have ever been on the planet have went extinct. And if we think about becoming well adapted, we've really got to think about how we fit into those strategies and how we fit into the rules of nature and what that starts to look like. So how do we do it? Well, you got to get out there and check things out. You got to tap into biologists to do that sort of work and figure it out. And I'll kind of close with this. I believe it's our responsibility as designers to do this differently and to kind of lean in and think about the way that we've been designing things. It's the only way that we're going to actually lead to something that's more resilient, more regenerative, and actually kind of allows us to continue to exist on the planet. So that's all I got. Thank you.
Thank you, Denny. This was fascinating. I think we have some time for maybe one or two questions. Mm-hmm. Maybe the first one that you kind of touched upon at the end is kind of, can you talk about how you actually do this, the process by which you do this, and like how do you decide which nature's system you're gonna even go to?
Yeah, so it's really about working with biomimics, so someone that's trained like I am that can help translate between the biologists and whatever that practice is. So a lot of times we're translating into software design or we're working in the built environment, et cetera. But it is also really about having biologists that can help you do functional biology. Most biology done today is very narrow and done for academic purposes. So in order to be able to tap into that and abstract those design principles out there, we use kind of an army of biologists that help us get to that. And we ask that question, how would nature solve this problem?
That sounds very impressive, having an army of biologists at your disposal. Maybe the other question is that in kind of these very research-heavy disciplines, I think it sounds like biomimicry is a very research-heavy discipline. What are some of the key steps that you have to take in order to actually move past that research phase and build something that is actually marketable and
Yeah, when you work with those biologists, you end up with a large set of that. And it is somewhat research intensive at the beginning of it, right? But it's one of those things where we're going slow a little bit early to go fast later. And then we narrow down kind of what the right solution is after we've asked that question, what would nature do? Then start to abstract the design principles out of that. And then it gets into a very common kind of design thinking methodology where you're starting with low fidelity prototypes, continuing to iterate, et cetera. And really those are, they're scaled to scale of project, whether we're working on just a small hard product where there are entire communities and city planning events that are happening actually with biomimicry. So those are a much longer horizon thing, much more processes. And it also depends on which disciplines you're working with. We move a little bit faster in the software space than maybe in the built environment space or the hard product space. So it's all on gradients according to kind of what the methodology and where you're working. Depends
on the context, yeah.
Exactly.
Well, anyway, this is fascinating. I'm sure that if anyone is interested, they can maybe pull you at the festival and ask you questions.
I will be around.
Thank you so much.
Thank you.